So pleasure mine today to present. Thank you for inviting and thank you for giving the opportunity to present the company. ATLANT 3D, we are based in Copenhagen. We develop unique technology, direct atomic layer processing technology. It's a modification of atomic layer deposition, ALD. So typically ALD done on a whole wafer, we do this locally. And we are based in Copenhagen. We have about 35 people with a focus on different applications, but primary focus is optics, photonics, and microelectronics, and emerging applications. So how we do today micro devices, it's a through lithography, so multi-step, different either deposition or etching and patterning. So it's, my opinion, quite complicated. So we decided to combine ALD with additive manufacturing approach and having benefits of both. So growth of various material, control at atomic scale, bottom up, digital control over the printed features and so on. And coming to ALD, there are two methods to do this. One is temporal ALD in a vacuum chamber with pulse by pulse processing. I believe I don't need to explain much about this. I believe many of you are engineers and know what is ALD, but there is another way to do spatial ALD, which can also work at atmospheric conditions. It's like a print head with the slots for each precursor and reactant to be delivered in separate zones, and then the substrate underneath moves and the deposition happens. So what we did, we made the micro nozzle, which has a centric geometry, and through this geometry we deliver ALD precursors to the surface, and one motion gives one atomic layer at a time. And this micro nozzle, it's about 16 by 16 millimeters. It's a microchemical ALD reactor, which is also replaceable. It can be different configurations of the nozzles, and the resolutions provides us a local ALD process. And here you could see this was our first article published in 22, where each letter was deposited with different thicknesses. As you could see, a lot of artifacts at that time. We already fixed many of them. And what we didn't expect is conformal and also very abrupt deposition, as you could see here from the lines of the process. And this basically gave us a possibility to control at atomic level each material and obtain patterns of any shape. So today the technology has several critical capabilities of direct patterning, local deposition, broad selection of material. It doesn't require vacuum, but we also work in vacuum. Micrometer scale line width. We recently demonstrated few micrometer line width. Since it's ALD, it can work on very complex surfaces, not only flat wafers, but membranes and nanostructures. And it allows also processing across the whole value chain from material processing to scalable manufacturing. So with this technology, we build an equipment and we compare this equipment as either can be integrated in the clean room, but also can substitute some of the processes. And we already validated deposition, of course, and then recently we demonstrated local etching. And we're looking now for local doping with our technology. And the equipment that we're building, it's integratable for glass boxes and cluster tools. So easy to work with existing infrastructures. So from our technology, as I mentioned, we do deposition, we do etching, we're looking into cleaning and doping, and then various applications that can be derived and built on this technology. We focus now on RF, printed electronics, sensor actuator MEMS, optics, photonics, advanced packaging. We now working on anamorphic sensing. Some quantum applications started to work. but the critical and the most interesting for us, it's a sensor and optics, two areas. So we work from material testing with very fast design of experiment to process structures, devices, and systems, including heterogeneous integration possibilities. So this is a list of materials that we have been validated. It's actually more than 15 now. This is the one that we have confidence that we can reproduce. A lot of other materials we are testing still, so I'm not advertising them. Mostly it's oxides. IMAC mentioned, I forgot who was that, sorry. Don't want to be impolite. So aluminum, titanium oxide, zinc oxide, iridium, hafnium oxide. We recently demonstrated gallium oxide and planning for niobium oxide also within the next month. What we do with this technology, we have flexibility in the thickness control, geometry control, gradient thickness control, roughness control, so we can easily modulate roughness. As you could see, this is comparison of two surfaces which we rastered. So this is completely flat with nanometer precision. This is with structures. We easily do have a flexibility over process development. So variation in the thickness, as you could see, from 5 nanometers, like 200, and the same wafer variation in the different temperatures that could be deposited. And this is one of the examples. So these structures were deposited on the same element. You might ask, well, how much time it takes to process? Depends, of course, on the micro nozzle, but 1 millimeter square, for example, if it's used with 360 micrometer nozzle, it takes like 1 minute to deposit, or 50 nanometers, 6 minutes. And the nozzle can be made like for 1 centimeter, also 1 centimeter wide. So it also would take 1 minute, but for 360 micrometers, it's like 40 minutes. So surface structuring, it's one of the key capabilities. So here you could see step-like gradient. It can be flat gradient, so very straight, or this type of structures. We can deposit over different type of surfaces. So here you could see silicon microgratings. This is black silicon. This is porous material. And this is just overview what type of surfaces we already deposited on. So random, micro, like membranes, or curved surfaces like for optics. One of the very interesting results that we recently obtained is by printing variable vertical, horizontal lines, we obtained like squares, as you could see here. And by varying different thicknesses, you could see different squares were achieved with different geometries. And the next, what we did, we tested this to basically modulate refractive index. So by varying geometries, not the material, we achieve different refractive index changes. So this is just overview to give you an idea what we did recently. So this is a direct rastered approach for hyperspectral gradient elements. This is two similar wafers that we did development with variation of the thickness of gradient of the thickness. This is for sensing elements like electrodes. This is for gas sensing. This is for electrochemistry. So we're looking into the areas where our optical capabilities, or optical material capabilities, can be used, like for optical filters, or for hyperspectral, or for meta surfaces, or for waveguides. And we can work on any type of substrates, not only silicon, glass, polymers, or gallium nitride, or silicon carbide. It really doesn't matter. ALD is quite flexible in that sense. And the capabilities that we the most interested is in optics and photonics. So just to highlight the development that we did with the gradient thickness filter, this is how we did. So we made bigger squares with one thickness, then we reduced the area for rastering to 5 nanometer thickness, 10 nanometers. We can really control it. It's like overnight process where nobody is engaged. We just leave it and the machine does the work. And in the end, you could see here the control over the thickness. We did the test measurements that confirming what we wanted to achieve. We did this with titanium oxide, but it can be done with any type of material, including metals, or like I say, there was a previous speaker interested in niobium oxide. Another very interesting test that we did. So meta surface and the surface modulation, basically. As you could see here, there are two functions that we implemented. One, it has this type of shapes. I don't know how to call them. Another was with just peaks. They can be as even as well as uneven. And it really depends on the geometries. And we, again, this is in automatic mode that we did. We did these measurements with imaging ellipsometry just to confirm that we obtained what we expected. Another development that we did recently with Silicon Austria Lab, it's local deposition on micrometers, where the request was to localize the titanium oxide in this area. It was actually successfully accomplished. So basically, working on a very sensitive diaphragms or any other very sensitive elements is quite also easy for us. We pre-program the area that we need to deposit, and then the printhead goes in that area and does the deposition. And another element which is less relevant to optics, but can be also applied, it's a heterogeneous sensor integration. You could see here all elements were done with the same process flow, electrodes with platinum, and the sensing element with different thicknesses with titanium oxide in one run. And how we do this, we have now Nanofabricator Lite, our core equipment that we also promote now, and Nanofabricator Pro. It's a 200 millimeter tool that we have the prototype in-house. That's what we use for development, and we finishing the industrial tool end of the year. And we just finished recently Nanofabricator Hub tool, which is which is staying in Switzerland with our partner in Lausanne. So happy to engage you. So how we work with equipment sales and also providing innovation as a service, so engaging with customers, providing from pilot to R&D, joint venture, joint development, or public funded projects, or contract manufacturing. And I would be happy to discuss any questions, and let me know if there are any interest to explore here.